Thank you very much. I would also like to start out by thanking the organizers for giving me a chance to talk here today, and in particular Mike Allen, who was my primary contact in this venture. So what I would like to do today is tell you a little bit about some recent work that we did on simple fluids that have an orientation dependence. And in particular, I would like to talk about isotropic to polar phase transitions in this sort of amphiphilic fluid. Now, this is the outline of my talk. I would like to give you a little bit of motivation why we are interested in these rather simple fluids that I will introduce in a minute. And then for most part of my talk, I will be focusing on this amphiphilic fluid, and will tell you a little bit about concepts of finite size scaling, which we are employing here to locate the phase transition and in particular to understand the nature of this phase transition. This involves the determination of the universality class of our system or our model, and of course this is based on an estimate of critical exponents driving this phase transition. So then I will give you a little bit of an insight into isotropic to polar phase transitions in this model, and very recently we have developed also a mean field theory of this phase transition that borrows ideas that have been used also by Margarita Telo da Gama and many other people. If I have time, I would like to switch to another variation of this model fluid that allows us to study simple liquid crystals. And in particular, we are interested here also in an order-disorder phase transition that takes the liquid crystal from the isotropic to a polar, to a nematic phase. And then I would like to summarize what I hope I could explain to you. Now, just by accident, my point of departure is the same one that has also been used by Professor Galindo yesterday. It's a simple fluid. The Lennard-Jones potential determines the interaction between two particles separated by a distance r12, and this potential only contains two parameters, namely the length scale sigma and the energy scale, which is determined by epsilon. Of course, this potential is isotropic, which is illustrated by this contour plot of the interaction potential. So what we do here is we fix one particle at the center and then move the other one around at some constant separation, and this generates this plot. And as you can see, if these particles approach each other close enough, there's an attraction between the particles. So just by having this very simple potential, you can generate phase diagrams that are actually realistic for key features of fluids, and I don't have to go into this any further because Professor Galindo yesterday explained that to you. Now, what she did then is to show you that if you go from a pure simple fluid to a binary mixture, you can actually generate quite complex behavior. Now, what we would like to do is something else. We would stick to the pure component fluid, but make the interaction more complicated. And that this can lead to very interesting behavior has already been demonstrated by these people here from Rome. And what they did is they took hard spheres that they decorated with patches, and actually they used the Frenkel-Kern model, in which the interaction between two patches is modeled by a square well potential. So what you do is, if you look at the interaction between two of these spheres, if the distance vector connecting the centers intersects the patches on both particles, you switch on the interaction. If this is not the case, it's just repulsive. And I don't want to discuss this in any detail, but just have you take a look at these snapshots. And as you can see, under certain conditions, you are forming fairly complicated structures like these micelles or lamellae, in this case, depending on the density. So we would also like to use a fairly simple model, again, based on the Lennard-Jones potential. But now we modify the interaction between our particles by some orientation-dependent function that I've indicated here. Now, in our case, the interaction between the molecules is determined by the orientation u1 and u2 of these particles and the distance vector r12. And in particular, this function is composed of two different parts. As you can see, the first one is that which describes the interaction between particles in a classical three-dimensional Heisenberg fluid. And you may also recognize the second part, which resembles the orientation dependence of an electrostatic dipole. However, in our case, the distance dependence is not long range, so the interaction potential decays as 1 over r to the 6, unlike in an electrostatic dipolar system where the decay is 1 over r to the 3rd. So because of the orientation dependence of our molecules, we have two distinct cases to consider. Particles can be aligned in a parallel fashion or in an anti-parallel fashion. So again, these are contour plots that we generated, in this case for a parallel orientation, and you can see that in this case, if the north pole of one particle is opposite to the south pole of the other one, then the interaction is rather weak, whereas if these particles are in this equator-equator configuration, the attraction is fairly strong. Now this picture changes if you consider the anti-parallel orientation. In this case, the strongest interaction is obtained if the north pole and the north pole of the other particle are facing each other, or the south pole and the south pole, as you can see from this contour plot. And the weakest interaction is this one, where the particles are aligned with their equators but are pointing in the opposite direction. So for most part of my talk, I will be presenting data that have been obtained in Monte Carlo simulations. We are using the isothermal isobaric ensemble, in which the thermodynamic state of the system is determined by the number of particles that we keep fixed, the pressure, and the temperature. Now, if you're doing computer simulations, for most, at least we are not interested in modeling any specific material. So all the data I will show you are expressed in units of the Lennard-Jones sigma and epsilon, or suitable combinations of that. So if you are missing anything on the axis like units, there are no units because we are working in dimensionless units. So we want to study the isotropic polar phase transition in our system, so we need an order parameter to look at. And the order parameter that I will be using in the first part of my talk is this polar order parameter, where n is the preferred direction into which particles are pointing in if they are oriented. So if all these molecular orientations are pointing exactly in the direction of the global orientation, of course this quantity would be 1. If you have an isotropic distribution of these molecular orientations around anything that you would call an orientation vector, of course this quantity would be 0. Now this is actually a plot that we obtained in our Monte Carlo simulations as a function of temperature. And if you just look at these curves, they start at a very low value at high temperatures, and then they go up and approach relatively high values. And of course this is indicating that you go from an isotropic to a polar state as you lower the temperature. However, if you look carefully at these data, you will notice that in the isotropic phase, these numbers seem to depend on the system size. So these curves have been obtained for different sizes of the simulation cell, going all the way from very small, namely 300 particles, to relatively large, 10,000 particles, which is the curve at the bottom. So we analyzed this system size dependence based on earlier work done by Dan Frenkel and his former student Epenga, and using their results and extending it to our specific order parameter, we would predict that this polar order parameter depends on the number of particles as 1 over n squared. And as you can see from the plot, our simulation data seem to follow this predicted 1 over n squared dependence, except for the very smallest systems where there might be corrections that we didn't include. So where does this orientation dependence, or the non-vanishing polar order parameter in the isotropic phase, come from? Remember the interaction potential that I showed you, which favors the alignment of nearest neighbors of particles. So it's conceivable that you have a domain around a central particle in which the neighboring particles are aligned in such a fashion that they prefer the parallel orientation with this central particle. Now, since you're in the isotropic phase, the correlation length between this domain and another one is small, so they don't see each other. So there may be another domain with a different net orientation somewhere else in the fluid. And of course, you can repeat this, and you have many such domains. So if you had an infinitely large system, you would average over all these domains, and in fact, your order parameter would be 0. Now, in a computer simulation, you have a finite system, and of course, then this doesn't really average out. So there is some residual order even in the isotropic phase. Now, when you start doing computer simulations as a student, one of the first things that you learn is that you have to be afraid of finite size effects. This is certainly true unless you can develop some analytical theory to actually turn this disadvantage into an advantage, which allows you from the finite size behavior to extract information about the infinite system. And this is exactly what people like Kurt Binder and others have done many years ago, and these are tools to analyze computer simulation data in a quantitative fashion, and that's what I want to do now. Before going into that, I would also like to show you another quantity that exhibits a finite size effect, and that's the order parameter susceptibility. As you can see from this equation, this is nothing but the fluctuation of the order parameter, and you can show that if you approach a critical point, for instance, this little t is a reduced temperature that tells you something about the distance from a critical point. If this goes to 0, then you expect this quantity to diverge, and this exponent gamma actually is one of the critical exponents that we will come back to later. So in the thermodynamic limit, then this quantity should go to infinity. These are, again, data that we obtained in our Monte Carlo simulations for different system sizes. So again, this is the order parameter susceptibility as a function of the temperature here. And the bottom curve, these dark circles, have actually been obtained for a very small system containing only 300 particles. And as you can see, there's a weak maximum in these data. The peak is rather broad. So this is really an effect that comes about because of the finite system that we are using here. If you make the system slightly larger, for instance, these open squares here are data that we obtained for a simulation system containing 2,000 particles. You see two effects. Number one, the peak becomes more pronounced and more narrow, but it's also shifting. For the largest system that we could study, of 10,000 particles, the peak is even taller and narrower, and again, it is shifting. So this tells you the same story that we already saw before from the order parameter plots. There is a transition from an isotropic to a polar phase. However, if you want to locate the phase transition, analyzing these data becomes extremely hard, because you can see that these peaks are becoming narrower and narrower and narrower. So in your computer simulation, where actually dealing with discrete data points, you may actually miss the peak position altogether. So there should be another way to locate the phase transition in a more reliable fashion. Now, we would like to do this in terms of the moments of the order parameter distribution P, and you can make an ansatz for this quantity within this finite size scaling concept that I already mentioned, that goes back to people like Binder and others. So in this case, the finite size scaling ansatz would contain of an explicit system size dependence reflected by this prefactor here times a scaling function. And if you express the scaling function in terms of a reasonably scaled variable, then of course this m tilde here should be system size independent. And I already introduced this t, so t is a measure of the distance of the actual temperature from the temperature at which the phase transition would occur. Now, rather than directly looking at this quantity, it is much more useful to look at what is called a cumulant. And in fact, the cumulant that we are using is the ratio of the second moment of the ordered parameter distribution relative to the first moment of the order parameter distribution squared. So this can be recast in terms of the scaling functions using this ansatz that I just introduced. Now, why is this useful? Now, this is particularly useful because if you go directly to the critical point, this ratio will be system size independent. So if you are plotting these cumulants for different system sizes, what this equation tells you is that they should intersect in a unique point. And of course, the value of this cumulant at this unique intersection is model dependent. So these are plots that we got from our Monte Carlo simulations. Actually, it's more convenient to plot G2 minus 1 rather than G2 directly, because this quantity is changing over several orders of magnitude, and we are plotting this here as a function of the temperature. Now, there are two limiting cases that you can consider analytically. Suppose you are sufficiently deep in the polar in the isotropic phase, you would expect the order parameter distribution to be a simple Gaussian. So you can work out the expression for the first and second moment using this Gaussian approximation to the order parameter distribution, and then it is very easy to demonstrate that if you look at G2 in that limit, the value of G2 should be pi over 2. So this dashed line that you see here is actually pi over 2 minus 1. And as you can see, these data for various system sizes seem to converge to that analytic limit fairly nicely if you are sufficiently deep in the isotropic phase. Now, they approach this limiting value the faster the larger the system size is, as you can see from these triangles here, which correspond to the system size of 10,000 particles. For 300 particles, the approach of this limiting value is much weaker. On the other hand, if you go to the polar phase and you are sufficiently deep in that polar phase at low temperature, then of course your order parameter distribution can be approximated by a delta function. Again, you can evaluate this integral analytically, and what you get is that the ratio of the second moment to the first moment squared should be just 1. So if you are subtracting 1, then this quantity should go to 0 if you are sufficiently deep in the polar phase at low temperatures. And as you can see, these values are already fairly small, and they're even smaller for the larger system compared with a smaller one. So these curves are inverted, and they are inverted exactly at this point where they all intersect. And according to what I told you a minute ago, this intersection then allows you to determine the temperature of the phase transition. So you can just read it off at the intersection between this red line and the temperature axis in this inset. Now, if you want to learn a little bit more about the nature of this phase transition, which apparently is second order, then you should be able to determine the critical exponents that govern your model. So in that sense, the system size dependence that I already demonstrated becomes very useful, because you can now look at the order parameter for various numbers of particles, various system sizes. So it is very easy to verify if you look at ratios of the order parameter for different system sizes, and you take the limit at which you are exactly at the point of the phase transition. This becomes the ratio of these two particle numbers to the power which contains various critical exponents. So it is then useful to introduce a function that we call omega here, W here, which depends on the two particle numbers and the temperature, and that is defined as the log of this ratio divided by the log of the two particle numbers. Now again, if you go to the critical point, the particle number dependence just cancels out, and what you're left with is a ratio of critical exponents. So if you are studying this function omega W for various particle numbers, they should intersect in a unique point, and from that unique point you can read off the value of this ratio of critical exponents. Now this is what we got from Monte Carlo simulations. This is a plot of this function W as a function of this reduced temperature. And as you can see, if you do this for two different combinations of N1 and N2, they do intersect in a unique point. So on the y-axis here, you can read off the value of beta over nu. Now what the inset shows you that you can take many other combinations and they all intersect in the same point, and that allows you to determine this ratio with sufficient accuracy. Now if you want to really determine absolute values of the critical exponents, an analysis like this would not do, so you need some way of determining the absolute value of at least one critical exponent. Now to that end, it is very useful to look at another function that I call u here, and that is simply the scaling function at some finite non-zero temperature T relative to the scaling function for the first moment of the order parameter distribution exactly at the temperature of the phase transition. Now it is easy to show that if you expand this in terms of the temperature, the leading term in this expansion would be linear in T times some constant A. Now what is this A? Now A can easily be identified by taking the first derivative of your scaling function with respect to the reduced temperature, and it turns out to be just the number of particles to the power 1 over 3 nu. So this then depends on just a single critical exponent. So if you are plotting the log of A as a function of the log of n, the slope allows you to determine the critical exponent that you are after. Now we've done this analysis based on our Monte Carlo data. So this is a plot of u as a function of this reduced temperature. And again, you see that curves for different numbers of particles do intersect in a single point at t equals 0. And if you look sufficiently closely around t equals 0, you see that these data can be approximated by straight lines, according to what I just told you. So you can now take the slope of these lines and plot the log of the slope as a function of the log of the number of particles. And by fitting a straight line to these data points, you can obtain the slope of this straight line, and the slope allows you to determine the critical exponent that you're after. Now you can invoke a third equation that is also well known as hyperscaling. Hyperscaling is nothing but an expression that relates these three critical exponents that we need here. And hyperscaling is nothing but a statement saying that in your problem there's just one characteristic length scale, and that is the correlation length. So if you combine all these different pieces of information, the hyperscaling relation, the ratio of beta over nu that you just determined from looking at the system size dependence of your order parameter, and this analysis that I just explained, you wind up getting a complete set of critical exponents, and of course that allows you to determine what universality class your model pertains to. Now, before I come back to the universality class, I would also like to indicate that if you are now using these critical exponents that you have determined and the scaling ansatz that I introduced a minute ago, you should be able to collapse your various data onto a unique curve if you express a properly rescaled order parameter as a function of the scaling function where the argument has been rescaled according to the ansatz. So these were the original data that I showed you, and if I apply this scaling ansatz, then they do indeed fall on a unique master curve as expected. So that tells you that apparently your critical exponents that you are using are reliable. These data do fall on this unique curve. There's also something else that you can do here, and if you look at the original data sufficiently deep in the polar phase, you will see that this system size dependence becomes less and less pronounced. So that means that under reasonable conditions, the order parameter becomes independent of the system size. And if you invoke your scaling ansatz, you can work out an expression that says, well, the order parameter should vary as the temperature to the power of one of the critical exponents. So in this representation, you would expect the data to approach this solid line in the polar regime, sufficiently deep in the polar region, but still in an area where the scaling ansatz should be valid. And as you can see, there is a nice convergence of the computer simulation data to this predicted solid line. You can do the same thing also for the order parameter susceptibility that I introduced a few slides before. And again, if you apply the scaling ansatz and work out the expressions, then this rescaled order parameter susceptibility as a function of the rescaled order parameter gives you a unique curve. And again, sufficiently deep in the polar phase where the scaling ansatz is still valid, they should converge to this solid line, and as you can see, they do. You can also apply finite size scaling to the order parameter distribution directly, which you can determine in your computer simulation as a histogram. And these are the original data for 10,000 particles all the way down to 300 particles. And as expected, you see that the peak is shifting, the peak form is changing, but you also see that there's only one peak if you are directly sitting at the point at which the phase transition occurs. At the end of my talk, I come back to this feature, which is indicative, of course, of a second order phase transition, and I hope I have time to compare this to other data where the phase transition is actually weakly first order. So applying the finite size scaling to these data, which vary quite a bit over a certain range of values of the order parameter, again, you get a unique distribution. The scatter is a bit larger here. That may have two reasons. Number one, you're actually looking at a histogram rather than an integral quantity. And number two, there should be corrections to this very simple finite size scaling ansatz that we neglected in this work. So that brings me to a first little summary. So I hope I could tell you that this finite size scaling, if it should be successful as a primary ingredient, needs an accurate value of the temperature at which the phase transition occurs. This we can get from this cumulant analysis as I demonstrated. If you determine the critical exponents, this allows you to determine the universality class, and in our case, the universality class turned out to be that of a 3D classical Heisenberg fluid. And that this is really the case, you can see from this little table where we get values for the critical exponents beta, gamma, and nu, and these are the data that we obtained, and the best data that I could find in the literature match our results quite nicely. So this confirms the universality class of our model system.
Can you remind us of the interaction? You had a Heisenberg part and a dipole part.
Right.
What was the form of the dipole part? Was it the usual 1 upon r cubed?
Except for the distance dependence. The distance dependence is short range rather than long range as you would have on an electrostatic dipole.
Yes.
But you are absolutely correct that these two ingredients in the model potential. And I come back to this a little later. So you can repeat the analysis for various pressures, and what you get is a line of critical points separating polar from isotropic phases, and this is analogous to the Curie line in ferroelectrics. Now, we wanted to look at this phase transition in a little bit more theoretical fashion. So what I'm trying to do now is familiarize you with some key concepts of mean field theory that we have been using here. So the first thing that we want to do is rewrite the expression for our model potential. And it is very convenient to do it in such a way that you introduce what is called spherical invariance. on account of the symmetry of the Heisenberg and the dipolar term, two of these spherical invariants enter our description. Now, what is a spherical invariant? This is nothing but a linear combination of various spherical harmonics times some Clebsch-Gordon coefficient, so we can work out an explicit expression for these objects here. At this point, it is worthwhile noting that spherical invariants form a complete orthogonal set of functions, and then you can use all the nice properties that you know about complete sets of orthogonal functions once it comes to integrals over orientations. And as you can see, this combination of three spherical harmonics depend on the orientation of molecule I, the orientation of molecule J, and the relative orientation of the two molecules. So the starting point is something that Bob Evans already explained to you. This is an expression for the change in free energy as you go from a reference system to your system of interest. So the reference system here is a hard sphere fluid where the interaction just depends on the distance between the centers, and coupled to that is our model potential, which has the full orientation dependence that I explained to you a few slides before. Now there's a coupling parameter, lambda, that takes you from the reference system for lambda equals 0 to the system that you would actually like to study. Now this expression that I've written down here assumes that in general the system is inhomogeneous and isotropic, so the orientation-dependent local densities of particle 1 and 2 enter this expression. And an additional assumption that we are using here is that we restrict the interaction to pairwise additive interactions. And they are, so the correlation between particles is given by this pair correlation function, which depends on the distance vector between the particles, their orientations, and of course the coupling constant lambda that I explained to you just a few minutes ago. Now, I already told you at the beginning that we are interested not in a simple mean field description, but a modified mean field description. That means our pair correlation function is 0 if the two particles are separated by less than the hard core diameter, and they are decaying with distance like this exponential if the separation is larger than the hard core diameter. So this expression here would be exact in the limit of vanishing density. Of course, it's an approximation if you're using it for arbitrary densities. But it has the nice feature that if you're using this form, you can perform the integration over the coupling parameter analytically. And this is an expression that Bob Evans already showed you on Monday, which involves the Meyer function, which now depends on the orientation of the particles rather than the distance. So we need a few more approximations here. We are working in the bulk, which means that the local density can be factorized in the following way. It is composed of the number density, which is position independent because you're working in the bulk, times this order parameter distribution that I call alpha of omega. Now, because this is a distribution, it should be properly normalized, and because of the symmetry of the polar phase that you are investigating, you can expand the order parameter distribution in terms of these Legendre polynomials that depend on the cosine of the angle between the global orientation of the system and whatever orientation you may have from the molecules. Of course, this would be 0 in the isotropic phase, so these alpha parameters, which are expansion coefficients, have the physical meaning of order parameters in this description. Now, after 60 pages of handwritten derivations, you finally arrive at a very simple expression for this change in the free energy. So you can write this as a density prefactor times this very simple looking infinite sum containing quantities that I call UL. And I will tell you what UL is in a minute. However, I would like to emphasize that in an isotropic system, you always have this contribution, and in a polar system, the leading term would be proportional to U1 and alpha 1. And this has been shown by Groh and Dietrich quite some time ago for an electrostatic dipolar system, and we're using their analysis to restrict our treatment just to this leading term. So what is this U1? U1 can be written as an integral over a quantity which is called F110, and this F110 is nothing but your Meyer function times the spherical invariant and then integrated over all the orientations. So that if you're using a high temperature expansion of the Meyer function, this finally gives you one as integrals over the isotropic part of your model potential. And the isotropic part, just to remind you, is the Lennard-Jones potential. So this cannot be done analytically, but you can do it numerically. So a little bit more about this. How do you locate a phase transition within this approach? Well, you realize that your total free energy is composed, of course, of the free energy of the reference system, an ideal gas term, and this quantity that are called delta Fx, which describes the interaction part in your model. So you can group these various contributions in terms of those depending on the isotropic part of your interaction potential and the anisotropic interaction potential. So if you're introducing a quantity I call delta F, which just subtracts all the isotropic contributions, then of course if you're in the isotropic phase, delta F would be 0. So as long as the isotropic phase is stable, this delta F would always be 0. So any small deviation from 0 would indicate the onset of order in your system. And you can use this to derive a very simple criterion in terms of this quantity U1. So as long as this vanishes, you are still in the isotropic phase. If it's no longer 0, then you are entering the polar phase. So if you rearrange this, then you wind up getting a closed expression for the critical density in terms of this numerically evaluated quantity U1. Now, how does that compare with Monte Carlo simulations? Well, first we need the critical temperature, which we get from the cumulant analysis, and then we use a linear interpolation of our MC data to get the associated critical density. And this is a plot of rho versus T, and as you can see here, for different system sizes, there is no system size effect in the densities, so you can use this to actually locate the critical density associated with this critical temperature. And these are the results that we obtain. So this ratio of critical density over temperature is here plotted as 1 over the coupling constant of the Heisenberg term, and I will say a little bit more about that later. So in this limit, you go to strong coupling. In this limit, you have weaker coupling. And these are the MC data that we obtained in comparison with this modified mean field theory. And as you can see, for moderately strong coupling constant, this modified mean field theory seems to be working quite nicely. As you go to weaker coupling constants, then of course the agreement is not that nice. There's a reason for that. We have a poster outside, and I can explain that reason if you are interested. It is basically that two of the assumptions that we have been making in deriving the mean field theory are not valid in that limit. What we are also plotting here is the prediction of a simple mean field theory, and the simple mean field theory just works like this. The pair correlation function is 0 for every separation smaller than sigma, and it is just 1 for larger separations, and that allows you to work out an explicit expression for this ratio, and that's where we are plotting these data as 1 over the coupling constant of the Heisenberg term. Now, I told you at the beginning, and I think I still have some time to tell you about another variant of our model potential, and that mimics a liquid crystal. And as you can see, it's basically the same potential, except for we replace this orientation-dependent function by another orientation-dependent function, which consists of combinations of second Legendre polynomials. Now what is important here is not the functional form of this thing, but rather that you have a certain symmetry, meaning that P2 of x is equal to P2 of minus x, and that allows you to model systems that have head-tail symmetry, and that of course is characteristic of liquid crystals, at least simple liquid crystals. Again, this is a contour plot of the interaction potential, and again, as you can see from the color code, this side-side configuration wins energetically over the end-end configuration, again something that is characteristic of liquid crystals. We need an order parameter. I don't want to go into the 19th or 20th definition of the Q tensor. All I want to say is we are focusing on two of the three eigenvalues, lambda naught and lambda plus, and the largest one, if ensemble average, gives you the nematic order parameter. So the results are plotted here, not as a function of temperature, but this time as a function of pressure. You can see the isotropic phase, where the value of the nematic order parameter is relatively small, and the nematic phase, where it is relatively large. Again, there's a pronounced system size effect, very similar to what you saw before for the polar order parameter in various in simulations containing various numbers of particles. There has been a prediction that was worked out by Dan Frenkel and Epenga in 1984 that allows you to look at the system size dependent of various combinations of lambda plus squared, lambda naught, and lambda naught squared. And according to Epenga and Frenkel, they should follow a certain scaling behavior. And as you can see, our data follow that scaling behavior over the range of system sizes that we could study here. Again, you can look at response functions, susceptibilities. In this case, we were looking at the isobaric heat capacity, which can be expressed in terms of fluctuations of this enthalpy, and these are plots of Cp versus P. Again, here you are in the, sorry, this is wrong. You should be in the nematic, no, in the isotropic phase at low pressures and in the nematic phase at high pressures, and in between this quantity passes through a maximum, just like the order parameter susceptibility before. This maximum shifts and becomes taller as you go to larger and larger systems. Now, if you analyze the peak position here as a function of the number of particles, you will find that the data fall in between what you would expect for a second order and a first order phase transition. Now, the analysis here is a little bit more complicated because Nigel Wilding showed that this does not really scale as n to the mu, but there's also a system size independent background that you have to take into account, and we did that in fitting those data. What this plot suggests, however, is that the phase transition is not really strongly first order, but maybe weakly first order, and I will try to give you some more evidence a little later. Again, we are looking at various cumulants. In this case, the one for the largest and the middle order parameter. There are effects that immediately follow from the scaling behavior. In this case, G2 plus does not depend on the system size, whereas G0 does depend on the system size. So this quantity is much better to use in locating the point at the phase transition. These are plots of these quantities as a function of pressure, and you can see they go through a unique intersection, and this intersection can be located much more easily from these data. Now, if you remember what I told you at the beginning about finite size scaling, if these curves intersect in a unique point, this would suggest you are looking at a second rather than a first order phase transition. Now, you have to be a little bit careful here. In order to find out whether you are actually at a second or a first order phase transition, you might want to look at the correlation length. Now, consider two particles that are close by, so their orientation might have a certain correlation. So if you move one particle to a larger distance, these become uncorrelated as indicated. So a measure of correlations in this arrangement would be the cosine of the angle between the orientation vectors u1 and u2. And we already saw this expression on one of the previous days. So if you are looking at this correlation function at large separations, this should go to the nematic order parameter squared. These are plots of G2 as a function of distance. The curves look pretty boring, but what I would like to indicate is that at sufficiently large distances, they do indeed go to the nematic order parameter squared. Now, if you subtract this quantity, and if you are looking at short-range correlations, then this quantity G2C should decay as an exponential, where L is the correlation length. So if you analyze your data at sufficiently large separations, you can use this expression to actually estimate what the correlation length should be. And for us, and two data sets just around the point of the phase transition, the correlation length is still fairly small, which seems to suggest that we are not looking at a second, but rather a first-order phase transition. Now, there's a problem, because if you work out your finite size scaling analysis for first-order phase transitions, you would find that pairs of cumulants here expressed in terms of the linear extension of your system rather than the number of particles should intersect in a unique point. So there are many of these points, and you can work out an expression for the pressure in the infinite system at which you have the transition in terms of the pressure in any finite system, and then there's an explicit system size dependence like this one. Now, Binder and co-workers have looked at this system size dependence for an isotropic nematic phase transition in a lattice polymer system. And what you see here is a plot of the transition temperature as a function of the number of lattice sites. And what you can see is that only for fairly small lattices, you have an appreciable system size dependence like the one that I tried to introduce here for the pressure rather than the temperature. As soon as you go to sufficiently large lattices in their data, there is no such system size dependence. So you may actually look at a first order phase transition, but your system is already sufficiently large that you do not see the system size dependence of the transition temperature, and that is what we believe is the case in our system too. So that would suggest that the isotropic to nematic phase transition is very weakly first order in the model that we are studying. So there's further evidence for this, and I told you at the beginning I would like to return to looking at order parameter distributions for these two different model systems, which differ only by the orientation dependence of the interaction. And this is for the amphiphilic molecule that I talked about at the beginning across the phase transition. So in the isotropic phase, you have this peak here, which is centered at 0. And the only thing that happens is as you go towards and across the phase transition, the peak shifts, becomes taller, and but it stays a single peak all the way across. So this suggests if you express your free energy in terms of the order parameter distribution, that all the time you have a single minimum, which would be indicative of a second order phase transition in agreement with the finite size scaling analysis that I explained at the beginning. However, in this liquid crystal system, something else happens. First, you're starting out with an order parameter distribution that has just a single maximum, but as you approach the phase transition, this splits into two maxima, and directly at the phase transition, these maxima become equal in size. So that means that you have a double free energy minimum at the phase transition. The fact that this is shifted away from the value 0 is again indicating that you have finite size effects, but it also indicates that this is the typical behavior of a first order phase transition in agreement with our conclusion from the finite size scaling analysis. So this is the summary. I hope I could convince you that this anisometric Lennard-Jones potential might be useful in modeling systems that have an orientation-dependent interaction at a very low computational cost. I demonstrated that for this amphiphilic fluid. This behaves essentially like a ferroelectric system. we determined the set of critical exponents, and from that we could conclude that the model pertains to the classical 3D Heisenberg universality class. In fact, it's interesting that Weiss and co-workers have done a similar analysis for an electrostatic dipole where the interaction is long range, and they could also conclude that their model belongs to the Heisenberg universality class. We developed this modified mean field theory, which is in good agreement with the Monte Carlo data. There's no influence of the dipolar term, so you may have wondered why I didn't even talk about the dipolar coupling. Those people experienced in dipolar systems would immediately know that. Our interactions are short range, so you wouldn't expect any influence of this dipolar term. More details can be found on the poster outside. For the liquid crystal system, the isotropic to nematic phase transition is weakly first order, and this seems to suggest that the symmetry of the interaction dictates the nature of the phase transition, at least in our model system. There are a couple of papers that came out on various aspects that I have been covering today. I have to thank my friend and co-worker Sabine Klapp, who was very instrumental in developing this modified mean field theory. My students who have been involved in various aspects of this work. There was funding, and of course I thank you for your kind attention and your patience with this talk. Thank you very much.